A very warm welcome from my side, dear customers, here in the booth, in the stand of Festo here in Esslingen. And you see me standing here in an apple tree. And what I told you when we started the virtual exhibition of Festo, the first virtual exhibition, is surprise me. And here in the future concepts, you will see surprisingly concepts in bionics from Caro and as well from Michael in motion, in SupraMotion. So these surprising concepts for the future, they are for you, for your applications in the future, for your energy consumption and for your applications that needs in the future innovations and therefore surprises. Caro, surprise us.
Yes, I'll give my very best, Martin. Thank you for the warm welcome. I am Caroline von Heven, Head of Corporate Bionic Projects here at Festo. Together with me are two engineers of future concepts. We have Mart Moerdijk from the Bionic team and Michael Schöttner from SupraMotion. We are very pleased that we got the chance today to introduce to you our latest future concepts. A changing industry requires a new way of interaction of people, machines, and data. In the factory of the future, humans and robots will work together more and more closely. Whether it's faster lead times or shorter production cycles, the requirements to the factory of the future are manifold. Imagine a system that could relieve workers from dangerous or monotonous tasks. A system that can act in an environment where people do not want to work because it's dangerous or of limited accessibility. Therefore, Festo has been looking intensively for a system that can relieve people from dangerous work and at the same time pose no risk. We came up with an electric mobile robot and a pneumatic gripper hand, a system that works autonomous and self-sufficient, including all the energy supply on board. It can be used for different tasks in a changing environment. So here it comes, our bionic mobile assistant. It was developed in the Bionic Learning Network together with the ETH in Zurich in Switzerland. It consists of 3 subsystems, as you can see here, the mobile platform, with a very unique drive concept. The ballbot balances on a ball. 3 so-called omni wheels, as you can see here, can set the ball in motion, so it can maneuver in any direction. An optimization program calculates how the ballbot and the arm must move to keep the hand in target position. The planning and control algorithms run on this computer here inside of the robot. We have a camera for localization, so it can do an autonomous way. Second, we have an electric arm. 4 so-called dyno drive operate this, in the shoulder and in the elbow. These are fully integrated motors, including gearbox, electronics, and sensors. And then we have the bionic soft hand, a pneumatic gripper modeled after the role model of the human hand. We have introduced this already last year, but added more features. Now we got a wrist for an optimized action of radius and flexible bone structures for a more precise interaction of the fingers. We'll see this later. Also, we added a lot of sensors for both visual and tactile object recognition. So maybe we can have a look through the eyes of the robot on this tablet. Maybe you can show this. Now the robot identifies an object, let's say an apple in this case, and now sets this as target position. He will try to grasp the apple completely by itself. Now he focuses the apple and grasps it. This is just an example for a task that can be fulfilled by such a service robot system. So Mart, I think, he likes you, brings you the apple. Can you show us maybe more details of the bionic soft hand?
Yes, I can. Thank you, Robert, and thank you, Caro.
Thank you.
I'm Mart Moerdijk. I'm a robotic engineer within the Festo Bionic Learning Network. and I've been working on the Bionic soft hand the last year. We did improve this hand as with respect to the last year with several key components. So one thing that stayed the same is a valve terminal that you can see here. It has 24 proportional piezo valves. It's highly integrated and it's uniquely packaged in a small valve terminal here. We use this to control 12 degrees of freedom, 2 of which are in the wrist to move down and up and to the left and the right. Then we have one in the thumb, actually to move the thumb in, and out, and the same for the index finger, it can move in and out. Then we have the top part of the thumb that can move in, and the bottom part. The same for the index finger, and the rest of the degrees of freedom are in the other fingers. So another thing that we improved is actually the bone structure inside the fingers. So previously we had completely flexible fingers, and this gave us some problems when picking up heavy objects. By adding this flexible bone structure, it also gives us the opportunity to integrate position sensors in the fingers themselves, but made it possible to actually get the position of the fingers more accurately. Another unique feature that we added is this glove. This was developed with an external partner within the Bionic Learning Network, and this glove adds a sense of touch to the robot. It has 131 sensor points, which can actually measure the force that is applied to the glove. As you can see here, if I press here, you can see on the screen that the value of the pressure that is measured changed, and it's also displayed on the screen. All this data that is gathered in the glove of all the sensors of the glove but also the sensors in the fingers and the camera is all sent to the computer that runs in the background, and we can use this computer as well to control the hand. Let me show you here what we can do with this. So we have, of course, you can think of a lot of different applications, and one we have made here. So if I press start, you can see the hand can go down and touch objects. And then you can actually here also see the forces applied to the sensors. And we can not only visualize this on the screen, but we can actually also apply the things that the hand feels to your own hand. So we have an array of speakers, ultrasonic speakers here, coupled with the camera. The camera can track your hand, and actually using the speakers can apply a force on your hand with focused ultrasound. So you can actually feel what the robotic hand also feels. And this can be useful in remote manipulation tasks, where you can manipulate the hand, but also feel what the hand actually feels. So we have like a touchless sense of a touchless force, basically.
Wow. Thank you for these wonderful insights in the Bionic soft hand. Touchless. This leads us directly to the next topic, SupraMotion and levitation. It's all about floating motion. Michael, you know more about this. Would you like to explain some details to us?
Yes. Caroline, thank you for this nice transition. And hello, ladies and gentlemen. I am Michael Schöttner, and I am the leader of the SupraMotion team at Festo. And today I want to inspire you with levitation. So, why levitation? Think about your production in the future, and think about that your products maybe need clean rooms, need a production free of particles. And if you want to be free of particles, you have to be free of friction, and free of friction means levitation. So let me show you our solution. I will introduce you our Supra modules. This is a system which is free of friction. We can realize big air gaps, we have no hot surfaces, we can mount actuators on the platform, and something more. And let me tell you how we do it. So, first of all, you have to make levitation. And maybe you know Festo and levitation means superconductors. Let me show you on this demonstrator. We use high temperature superconductors here in this chamber, and these high temperature superconductors have some fancy behaviors. One of these behavior is that they can store magnetic fields. And how does it work? You take this Supra module, and inside of the Supra module, we have a strong permanent magnet system. You take a spacer between the Supra module with this distance you want to levitate, and then you cool down the superconductor. And if the superconductor reaches his superconductive temperature, it's for high temperature superconductors approximately minus 180 degrees Celsius, the superconductor stores these magnetic fields and fixes this permanent magnet in all direction. You can remove the spacer, and there's really a strong coupling between the superconductor module and the Supra module. So it's a pity that you not can be here and feel how strong this coupling is. So we need very low power to do that. So 30 watts is enough to carry more than 100 kilograms, and we cool it with an electric cooler. And we need no liquid gases and something else. So, but that's not all. We move this Supra module, and if you want to move this module, it is very simple to do because it is coupled with the superconductor unit. So you have only to move the superconductor unit, and the Supra module will follow the movement. So, but that's not all. We implemented separately power supply in the Supra module. And therefore we can mount different actuators, for example, this micro gripper. This micro gripper is developed especially for laboratory automation, and it is work absolutely free of friction. It makes no particle, and it has a very low power consumption. So, but other actuators are also possible, like dispensers or something else. And the control of the system is wireless. So for this micro gripper, we use IO-Link wireless. And you see, we have no cables. We have really big air gaps. We have no friction. We have no particles. And we have a very low power consumption system. Okay, I hope I have inspired you with our Supra modules. And it would be great if we can take part in your innovation process for your next production line. And remember, we develop concepts for the future, and together with us, your future can be now. Thank you for your attention. But there's just one little thing. I think the step from levitation to flying is only a little one for our bionic team. And I'm sure that our bionic team prepared some flying highlights for you. Caroline, it's your part.
Thank you, Michael.
Thank you.
Yes, in Bionic we get inspired from nature. And also this year we got inspired by a small bird, a swift or a swallow. So we came up with the Bionic Swift, which is a lightweight construction and weighs only 42 grams. Less weight means less energy consumption and allows for efficient flying maneuvers. Using 3D printing technologies, we can achieve optimized structures. But for efficient flight maneuvers, not only the weight is important, we also had a close look at the wing. This is modeled after the natural plumage of birds. Consists of single feathers that lie shingle-like over each other. During wing upstroke, feathers open, so air can flow through and save energy. During wing downstroke, it closes for an efficient wing stroke. But the most innovation with the Bionic Swift is the autonomous flight of artificial birds. Safe and coordinated flying maneuvers without a human pilot. We've never shown this before. For this difficult task, we invented a kind of indoor GPS on a radio basis, which is installed here on the booth. The birds fly on a given track, and if they are deviated from their track, they intervene autonomously in the situation and come back on track by themselves. This looks really impressive, and I would like to show this to you, the birds flying over the booth. So I hope you enjoyed the bird's flight. I know you can hardly tell them apart from their natural role model. I hope you got inspired a little bit, and now we're ready for your questions.
Definitely.
Martin.
Thank you very much. Thanks to you, not only our customers get inspired, but also, as I said, they were surprised. They were really surprised by all this knowledge, by all this work getting into a hand, or the work to make something fly, or the ball bot to make something roll. And also, when you look into applications like the SupraMotion application, this is very near, very interesting for a lot of applications today. Well, we do have a question, and let me see. What is the material used for the ball?
This is a good question. The ball was manufactured especially for this application. So from the outside, it's a rubber material, and inside, it's metal core. So it's not a good idea to play soccer with it.
So this will be quite hard.
Yes.
Very nice, very nice. So also very sturdy, right?
Yes.
If you have that, then
Carries the weight.
on a long lifetime and carries the weight.
Right.
Exactly. That's the beneficial. And we have another one. What happens with SupraMotion if power fails?
If power fails, this is a very interesting answer, and also easy to answer with nothing. So first of all, nothing happens because the superconductor is in a thermal insulated chamber, and it needs many time until he gets as warm as he stops with superconducting. So that means in our application, for example, we have more than 1 hour until levitation stops.
So here you can see that this superconductor material then means at the very end you don't need energy for this application. You only need coolant. That means if coolant fails, the superconductor effect will fail, but this takes an hour, as I have learned. Great.
At this application, an hour, yes.
Yeah. So thank you very much. Thank you for your questions. Thank you for being with us. And thank you to all the three of you making this a strong success, making this 2 days together with our customers, with our colleagues here on the booth, a success for Festo, for you, and having you here on our booth. This is what we are working for. Thank you. Stay tuned. This actually was now the highlight and the last session of today, the last live session of today. You may still go around the booth, have a look to other sessions we have recorded, and find your way and find your questions to the chat partners we have still on the platform. Thank you very much for being with us, and we would like to say thank you, stay safe, stay healthy, and take care.
Thank you.
Bye-bye.
Bye-bye.